Dear students, this part of Ray Optics and Optical Instruments part 3 is brought to you by VGuide TV. In this video, I'm going to discuss refraction through a slab and applications of refraction. You can watch class 10 light video part 3 for refraction and how the light is refracting from one medium to another medium. It is there in part 3 light video. Here I am starting with refraction through a slab. See, this is a glass slab. In this glass slab, the light is traveling from air to glass and from glass to air. If you see this, AB is your incident ray, BC your refracted ray, CD your emergent ray. This is your angle of incidence, angle of refraction. For the second interface, this is the angle of incidence and this is the angle of refraction. If you see the emergent ray, you can see that is displaced this much. This displacement, this perpendicular displacement is called by the name lateral shift. Now first I am going to prove that angle of incidence and angle of emergence are same. For that I am applying the Snell's law. Snell's law for the first interface, that is N2 by N1 is equal to sin I1 by sin R1, that is for this case. Second interface, the light is traveling from glass to air, so we can write N1 by N2 is equal to sin I2 by sin R2. If you see this, you can understand that these two lines are parallel. This is a transversal, so this I1 R1 is equal to I2. So we can write here R1 is equal to I2 because of alternate interior angle concept. Next you do one thing, you have to multiply equation number 1 into 2. If you multiply equation 1 and 2, we will get these two terms become 1. The same terms get cancelled and we get sin I1 is equal to sin of R2. Sin cancel. So I1 is equal to R2. It means that angle of incidence is equal to angle of emergence. Okay, now they may ask in some question, what is the displacement? Lateral displacement. This I told it can be called a shift or lateral displacement. For that, again I am just taking the triangle, two triangles, right angle triangle. That is, first I am taking this perpendicular distance is nothing but thickness of slab T. Another one what I am taking is this CF is your lateral displacement, and if you just extend the incident ray backwards, the angle made here is called the deviation. That means refracted ray, this much angle it got deviated. So I wrote here CF is called the lateral shift or lateral displacement, and next BE is called thickness of the slab. Angle CBF is delta, that is called the deviation. Okay. Now after that, what I am doing is I am going to take two triangles from here. What are the two triangles we are taking here? We have to take two right angle triangle. First one is CFB. Right triangle I am taking CFB. It's a perpendicular distance, no? So this will be a right triangle. So from this triangle, this angle is delta. So with respect to delta, I find sin delta. Opposite side by hypotenuse, CF by BC. Next you take this right triangle. This also it's a normal only, BEC. BEC. From here you find cos R1. Cos R1 is adjacent side BE by BC. So from this, you can take the value of BC, cross multiply. BC equals BE by cos R1. After that, I am substituting the value of BC. the value of BC in the first equation. So sin delta equals CF by BC is BE by cos R1. Okay. Next, cross multiply. CF equals BE sin delta by cos R1. Now we have all the values. CF is nothing but D. BE is nothing but thickness of the slab by cos R1 into. If you see this triangle again, this is your, what is this one? This is the normal. Okay, this red one is the normal. And see in this I1 and this are alternate vertically opposite angles. I1 and this full is vertically opposite angles. We know that vertically opposite angles are same. So we can write delta as I1 minus R1. So I did that only. In place of delta I wrote I1 minus R1. So this is the equation used to find the lateral displacement or lateral shift. Sometimes they may ask this lateral displacement. So in this lateral displacement, it is directly proportional to thickness of the slab. If the slab thickness is getting increased, lateral displacement also getting increased. Okay. Next, I am going for what are the applications of refraction. In that the first important application is, you observed a lot of time, a coin appears to be raised if we place the coin inside a beaker containing water. Or a water tank appears less deep than what actually it is. So I'm just taking an example. You assume it's like a beaker or a tank. Here I'm keeping a coin, an object I placed. Okay. So the distance of the top of the tank to the bottom is called by the name real depth. But due to refraction, I feel the object is here. So this distance is called by the name apparent depth. Okay. So what is actual distance, that's called real depth, and where we feel, that is called the apparent depth. So I am going to find out what is the relation between real depth and apparent depth. For that, I have taken another diagram, same diagram only taken in another form, that one ray is coming in the normal, another one, here it's our eye. Okay, you can take any rays. I have taken two rays. In that, with the second ray only I am explaining. So this ray is going here and it's getting refracted. I drawn a normal. So this will be angle of incidence and this will be angle of refraction, right? Angle of incidence, angle of refraction. Then if you extend this ray backward, as this is R, this also will be R, right? Now we know that this is normal, this also it's a normal, this is a normal line only. This and this are normal, so this is I, means this part also will be I. Then after that I am taking two angles, sin I and sin R. Sin I is opposite side by hypotenuse. That is, if you take this triangle, we can take the opposite side as AB by hypotenuse, I can take it as BO. If you take the upper small triangle for sin R, opposite side is AB only, hypotenuse is BO dash. AB cancel, so it will be BO dash by BO. Here we take an assumption that this C is not so far from, or this B is not far from A, because this ray should reach our eyes. So we are taking, as the pupil size is very small, the ray BC will enter our eyes only when B is close to A. It means that instead of B, you can write A. So your equation changes as AO dash by AO. Left side you check it. Here the light is going from denser to a rarer medium, or from water to air. So that's what we are writing, refractive index of air with respect to water. Refractive index of air with respect to water. That is sin I by sin R. That is AO dash by AO. If you want refractive index of water with respect to air, it is the reciprocal. That is AO by AO dash. AO is the real depth. AO dash is the apparent depth. So we will get an equation n equals real depth by apparent depth. Now everyone should remember, in this case I have taken your coin is inside the water. It means object in a denser medium. But where is the observer? In a rarer medium. So in this case your apparent depth is lesser than the real depth. So you can take apparent depth is lesser than real depth. But there are situations in which real depth is greater than apparent depth is greater than real depth. It's just opposite criteria. Object should be in a rarer media and observer should be in a denser media. For example, assume that a person under the water is observing a bird flying in air. So observer is inside the water, but bird is an object in air. So object in a rarer media, observer in a denser media, and observer is feeling the bird is more far from the actual distance. So there are situations. So remember the equation n equals real depth by apparent depth. We all have come across with this situation that we feel a coin inside the water appears to be raised. We feel that the coin is near, but if you want to touch it, it may be more far. Okay, next. Another one I want to discuss about our atmospheric refraction. Due to atmospheric refraction only, the sun is visible before actual sunrise and after actual sunset. Okay, the thing is, as the height increases, refractive index decreases. The light rays starting from the sun travel from a rarer to denser layers. They bend more towards the normal. It means this is your sun. Actual sun position is here only, below the horizon here. This is your earth. But what we feel is, as the density of different layers are different, refractive index of the layers also different. So as due to the variation of the refractive index of the layer, these rays undergo refraction. So we feel that the sun is here because the rays are bending like this and going. This bended rays, if you extend it backward, here is the object we feel, but actual object is not there. So an observer standing on the earth, the sun which is actually in a position of S below the horizon, but it appears a position of S dash above the horizon. Thus the sun appears to rise early by 2 minutes and it appears to set late by 2 minutes. It means that total we feel 4 minutes difference. This is due to which phenomena only? Atmospheric refraction. Why atmospheric refraction is possible? Because as the height increases, refractive index is getting decreased. Okay, it means that when we come near to that, refractive index is increasing and refracted ray bend towards the normal. Even twinkling of stars also, it is based on atmospheric refraction only. Twinkling of stars also based on atmospheric refraction only. Here also, when the rays enter into the earth atmosphere, they have to come across a medium of varying refractive index. Because of that, we feel like the stars are twinkling. So what all I discussed just now, they are the applications of refraction. So the first one is we feel like that apparent depth, real depth. Apparent depth, real depth means we feel that a water tank appears to be more deeper than what exactly it is. And atmospheric also act as a medium of varying refractive index. So here also many atmospheric phenomena also it's due to atmospheric refraction. This means, for example, like advanced, we can see call it as like advanced sunrise and delayed sunset. Advanced sunrise and delayed sunset is also due to atmospheric refraction. And just now what I told is twinkling of stars also atmospheric refraction. Okay. Thank you. Subscribe for more videos of class 1 to class 12 VGuide TV channel by VGuide TV. Thank you.